When the James Webb Space Telescope, or JWST, started sending back its first images, the astronomical community was electrified. Here we were looking at some of the earliest galaxies ever formed in the universe, galaxies that existed during what we call cosmic dawn, less than 1 billion years after the Big Bang. These galaxies were seen as impossible for their time, so huge and luminous that they seemed to defy the very laws of cosmology. For a brief moment, it seemed that everything we thought we knew about the universe's formation could be wrong. To put this into perspective, the standard model of cosmology, known as the Lambda Cold Dark Matter model, or LCDM, has been the bedrock of our understanding of the cosmos for decades. This model explains how the universe has expanded from the Big Bang, how galaxies formed, and how dark matter and dark energy have shaped the evolution of cosmic structures. According to this model, the first galaxies were expected to be small, modest collections of stars, forming slowly over time. But what JWST saw seemed to defy this expectation. Instead of small, fledgling galaxies, it revealed a universe teeming with massive, bright galaxies, far earlier than they should have existed. Naturally, this discovery sent shockwaves through the world of astronomy. If these galaxies were truly as massive as they appeared, it would mean that our understanding of how galaxies form and evolve was fundamentally flawed. Some even called it another crisis in cosmology, a term that has been used before when key discoveries challenge the established models. It wouldn't be the first time the field of cosmology has faced such a crisis. But this time, the implications were massive. Could it be that the LCDM model, which had so successfully explained so much about the universe, was no longer valid? Were we about to rewrite our understanding of the cosmos from the ground up? For months, this question hung in the air, driving debates, discussions, and further investigations. Scientists from all over the world started to re-examine the data, looking for clues that could explain how these galaxies got so big so quickly. Some theorized that perhaps there was something fundamentally new about the early universe that we hadn't accounted for. Perhaps some unknown mechanism was accelerating galaxy growth in those early epochs. Others wondered if our models of dark matter and dark energy needed revisiting. But as is often the case in science, the initial shock eventually gave way to deeper analysis. A new study, led by Catherine Chorowski, a graduate student at the University of Texas at Austin and a National Science Foundation fellow, has now provided a much-needed perspective on these findings. Alongside a team of international researchers, Chorowski's study suggests that these galaxies were not actually as large as they first appeared. Instead, the confusion may have been caused by a phenomenon that astronomers are very familiar with: gravitational lensing. Gravitational lensing occurs when a massive object, like a black hole or a galaxy cluster, sits between us and a more distant object. The gravity of the intervening object warps space-time, effectively bending the light from the more distant object around it. This can make the distant object appear much larger and brighter than it actually is. In other words, some of these early galaxies might have been magnified by black holes or other dense objects, making them seem much more massive than they truly were. The light we saw wasn't just from the stars in these galaxies. It was also from the material falling into the black holes at their centers. This is a significant finding because it suggests that the apparent crisis in cosmology might not be a crisis after all. The LCDM model may still be valid, and the early galaxies observed by JWST were not actually defying the laws of cosmology. They were just playing a trick on us. Chorowski and her team found that when the light from these black holes was removed from the analysis, the remaining galaxies were much more consistent with what the standard model predicts. They were still exciting and significant discoveries, but they didn't require us to throw out our existing theories about how the universe works. This finding has brought a sense of relief to many astronomers and cosmologists who have spent their careers building and refining the LCDM model. As Stephen Finkelstein, a professor of astronomy at the University of Texas and a co-author of the study, put it, anytime you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out. And that's simply not the case here. However, even though the crisis may have been averted, this discovery has opened up new questions about the early universe. While gravitational lensing can explain why some of these galaxies appeared larger than they actually were, it doesn't fully account for the sheer number of galaxies that JWST has detected in these early epochs. There are still twice as many galaxies as the standard model predicts, which suggests that something unusual was happening in the early universe to accelerate star formation. One possible explanation is that stars were forming much more rapidly in the early universe than they do today. Stars form from clouds of dust and gas, which cool and condense under the force of gravity until nuclear fusion begins in their cores. This process is typically slow and steady, as the outward pressure from the heat of fusion counteracts the force of gravity, preventing the star from collapsing too quickly. But in the early universe, things may have been different. The universe was much denser back then, which could have allowed stars to form more rapidly by preventing the gas from being blown away during the star formation process. This idea is supported by earlier research conducted by Avishai Dekel and his colleagues at the Rasa Institute of Physics at the Hebrew University of Jerusalem. Dekel's team suggested that the early universe was filled with low-density dust clouds that allowed for rapid star formation. This would account for the large number of galaxies seen in the JWST data without requiring any changes to the standard model of cosmology. Essentially, the universe might have just been a more efficient star factory in its younger days. But there's more. The Sears team and other research groups have also been investigating the spectra of the black holes at the centers of these early galaxies. Spectra allow astronomers to study the light emitted by objects in space, breaking it down into its component wavelengths. This can reveal important information about the composition, temperature, and motion of the objects being observed. In this case, the spectra of these black holes showed the presence of fast-moving hydrogen gas, which could be a sign that these black holes have accretion disks. Accretion disks are swirling rings of gas and dust that form around black holes as material falls into them. The intense gravity of the black hole causes the material in the disk to heat up and emit large amounts of light, sometimes making the black hole appear even brighter than the galaxy it resides in. This could explain why some of the early galaxies in the JWST data appeared so bright. Much of their light might have been coming from the accretion disks around their central black holes, rather than from stars. This raises even more questions about how black holes and galaxies interacted in the early universe. Did black holes play a larger role in the early formation of galaxies than we previously thought? Were they more active, consuming gas and dust at a faster rate, and emitting more light as a result? And if so, how did this affect the evolution of these galaxies over time? These are the kinds of questions that astronomers will be grappling with in the coming years as they continue to analyze the JWST data and conduct follow-up observations. While the initial panic about the impossible galaxies discovered by JWST has subsided, the excitement hasn't gone away. In fact, this discovery has only deepened our curiosity about the early universe and the processes that shaped it. We may have resolved the immediate crisis, but we've also opened up new avenues of research that could lead to even more groundbreaking discoveries. Katherine Chorowski herself expressed this sentiment perfectly when she said, "There is still that sense of intrigue. Not everything is fully understood. That's what makes doing this kind of science fun, because it'd be a terribly boring field if one paper figured everything out, or there were no more questions to answer. Indeed, the beauty of science is that every answer leads to new questions, and every discovery reveals new mysteries to explore. The universe is vast, complex, and full of surprises, and with tools like the James Webb Space Telescope at our disposal, we're only just beginning to scratch the surface of what's out there. So while we can breathe a sigh of relief knowing that our cosmological models are still on solid ground, we also know that the journey of discovery is far from over. In the years and decades to come, we will continue to learn more about the universe's earliest days, how galaxies and stars formed, and the role that black holes played in shaping the cosmos. And who knows, perhaps one day we will face another crisis in cosmology. But when that day comes, we'll be ready to embrace the challenge, knowing that every crisis is an opportunity to learn, to grow, and to deepen our understanding of the incredible universe we call home.